with chapter 22, and for chapter 22 we are going to continue working with electric fields. We are going to learn a new method of calculating electric fields, and that is Gauss's law. It is connected to what we did in chapter 21. And the connected with the idea of Gauss's law is the concept of flux, and we are going to learn maybe in the first part how we are going to calculate electric flux. What's the meaning of an electric flux? We are looking here for determining the amount of charge within a closed surface by just examining the electric field on the surface. And then we are going to understand the meaning of electric flux and how we can calculate it, and how we can relate that electric flux to Gauss's law and to the charge that is enclosed by the surface, and in the same time calculate the electric field due to a symmetric charge distribution. Then I will say Gauss's law, it's very good for systems when we have charges that they are really continuous charges, and also they have a symmetric distribution. And if we have a conductor, we are going to look and find out where is the charge located. Now here you can see a child that is just touching the Van de Graaff here, and of course is gonna feel that it's gonna acquire some of the charge, and then that charge when it will reach his or her hair is gonna be like having the same or like charges, and because of that it will repel and stand out. Some of the questions that we might ask: what would happen if the child stood inside a large charged metal shell? Okay, and we will, by the end of we will answer this question, and we will find that we can use symmetry properties to make our study easier, and we will also, as I said, calculate electric fields using Gauss's law. Now here we have, let's say we have this box, and that box is just imaginary, and we can look at the electric field lines and find out what is going to be the charge enclosed within this surface and related to the electric field. And this is the idea of Gauss's law. Actually, it has to do with having a surface around a distribution of charges, and then we are going to relate the flux to that charge enclosed, and then we will be able to calculate the electric field. Now just here, if we can look at these here, these both boxes, they have positive charges within the box, and the positive charge, remember, if we want to measure or find out something about the electric field, we're going to imagine that we have a test charge here that is very small, that it will not disturb the electric field, and then we are going to ask how is going to be affected, of course, repulsion, and therefore we are going to find that the electric field lines here, they are going to be outward. And here the field buttons that we have in these boxes are different in detail, since the box on the left contains only one charge and the one on the right contains two charges. Okay, therefore like I will say, every point here is going to feel the effect of two fields. This one is going to have only one charge. Also, if we have negative charges instead inside these boxes, there is an inward electric field. And again, because if I will place here a test positive charge, it will be attracted. What happens if there is no charge inside the box? Then the box is empty, and I will say the electric field is zero everywhere, and we don't have any flux going into or out of that box. This is because I don't have charge. Also, what if I have one positive, one negative? Okay, and if I will look at the enclosed surface, which is here the box, I will find that the net charge, and of course they are equal, the net charge is going to be zero. And then here you will find that there is some of these lines are really flowing into the box, some are really flowing out of the box. And if we will count like exactly, we will find that the number of N equals the number of out, and then the net here flux is going to be zero. Also, what happens if there is a charge near the box? Okay, then again, we are going to find that there are lines that they're gonna enter the box, and the same number of lines they're gonna leave the box, and then the net flux is gonna be zero. What affects the flux through a box? The net electric flux is directly proportional to the charge, net amount of charge enclosed by within the surface. Then I will say here, if we have a charge that it is let's say 1 coulomb, then I will have the flux is going to be outward. And if I will double the charge, I will double the magnitude of the electric flux on the surface, because now the electric field is double of that in A. We will also know here that the net electric flux is independent of the size of the closed surface. And therefore, you're going to see that we will not be saying anything about the size of that Gaussian surface that we are going to have. Then it doesn't I will say, if I have a box and or another box that is really bigger, okay, I will say we will not have any effect because of the size. Now, in order for us to calculate the flux, we are going to consider a flat area that is perpendicular to a uniform electric field. And then we will say phi, which is the flux, equals E dot A. Remember, this is the dot product that is going to result in a scalar quantity. And we know that the magnitude of this, it is EA cosine of theta. Now, or phi here, okay, let me use phi, the same notation. And here, when I have the flux, when I have the electric field hitting the area perpendicular, this is the maximum flux I can have, and here we can say cosine 0 is 1, and this is the maximum flux. Something that I want you to know, that the area vector, it's a vector that is perpendicular to the to the area. It is not like here. If I have the area like this is a vector, and we will say it is A times the normal on that area. Okay, then if I have an area here, this is the area vector. Okay, it's always perpendicular. Now, if the area is not perpendicular to the field, then if your field lines pass through it, and we will say here, of course, my number is going to be less, because now my phi is going to be EA cosine phi, and that number is going to be a fraction, then it's going to reduce the flux. If the area is edge on the field, then the area is perpendicular to the field and the flux is zero, because cosine 90 is zero. When I have a non-uniform electric field, then I should do a surface integral, and that is, I will say the flux, it is E times cosine phi times dA, and then I just will take the component of E that is perpendicular to the surface, and I will find the vector element surface area dA and multiply it by E and then integrate. The unit for the electric flux, it is in newtons times meters squared. Okay, let me write it in Newton times meters squared divided by Coulomb. Now I will do some examples here related to, but like I need to rearrange my pages here. I need to bring my hopefully I will be able to do that, to bring okay, then this is one, and the second one I want to bring is this one here. Hopefully I did not disturb all the others. Finally, this is the last one. All right, and let's see here what I did. Of course, I made a mess. Anyway, okay. Let me do one of the problems here. If I have a spherical surface with radius r in a region of uniform electric field, and it has its axis aligned parallel to the direction of the field, calculate the flux through the surface. The flux, it is E times A, and I will say now if we are going to consider the surfaces here, this one is the flat one and this one is the curved one. The electric field line pass through the bottom surface here are the same as the numbers that pass through the curved surface, and therefore I can use the area, because this is the area here, it's a circle, and therefore I'm gonna write pi r squared, and that is equal pi r squared times E. Then this is really my answer, pi r squared times E. This is a very easy question. I will move to the next one. The next one, it is a cube that I have it here, and it has side that has a length of 10 centimeters. The electric field is uniform, and it has a magnitude of 4×10⁻�3, and it is parallel to the XY plane at an angle of 53.1. measured from the positive x-axis toward the y-axis. What is the electric flux through each of the 6 cube faces, S1, S2, S3, S4, S5, and S6? And what is the total electric flux through all faces of the cube? Something here that I want you to know, what I was going to say, that my x is here. It's not, usually we use, my axis here. This is the x, this is the y, and this is my z. This is how really, the axes. Now for each of the surfaces, I will say E theta phi is the flux. It is E times A, and therefore it is E times A cosine phi. All what is really different here is the area vector. And the area vector, as I said, it is A times N, and always it is perpendicular to the surface. If you can look here at this S1 here, it is standing on the x-axis, and its normal is going to be minus j. And if I wish to calculate the flux, it is EA times cosine the angle between 90 minus 53.1, and that is 36.9. And if I will plug my numbers, it's going to be negative 32 Newton times meter squared divided by Coulomb. I continue here the same idea, and for S2, it is the one on the top. Therefore, its area, it's along the Z, then it is K. And therefore, it's going to have cosine 90, which is 0, and then the flux here is 0. Also, when I move to NS3, it is on the other side of the X, and it's going to be the same flux like S1, but it is going to be a plus 32. S4, it is similar to, to S2, and therefore it is cosine 90, and therefore it is 0. And when I look at S5 and S6, they are really along the I, which is the X, and therefore I will say one of them is going to be 24 and the other one is going to be negative 24. If we will add all of these, the net flux is going to be 0. Now, thank you. Here, I think I'm going to stop here, and then I'm going to continue with the second video.